Step into a room that is almost dark. On a bench, a tiny sensor waits silent, patient. Then it happens. A single tick. One photon arrived, met silicon, and left a trace. That soft click is more than sound. It is the moment a possibility became part of the world's ledger. Far away, in the long tunnels of LIGO, lasers paced between mirrors polished to a perfection the eye can't judge. A passing ripple in space-time, born from colliding black holes half a universe away, nudges one mirror by less than the width of a proton. The instruments answer with a tremor of light on a screen, and again the record grows. The cosmos has whispered, and we've written it down. Tonight's story begins with those records, because in the quantum world, before a trace is made, an electron is not here or there, but poised between outcomes, a mist of possibilities. And yet the instant a detector clicks, the haze clears. The experiment has chosen. What changed? What turns maybes into one durable fact? We often say observer and pictures of watchful eyes follow, but physics is quieter and more honest. An observer need not be a person at all. A grain of photographic film, a crystal in a Geiger tube, a droplet in a cloud chamber, any of these can notice. To observe is to leave evidence, to catch, to copy, to amplify a microscopic event until it becomes a mark that will not easily fade. The world observes itself all the time. We are its most curious witnesses, not its magical makers. Hold a single photon camera to the dark and wait. Each click is a commitment. Energy arrived here, now, not there, not later. Open the logbook and you'll see a constellation of such commitments. Tiny stars of ink that, together, sketch a picture of reality as shared experience. Between the clicks lies possibility. Across the clicks, history. But the clicks raise hard questions. Where, exactly, does observation happen? At the sensor's surface? In its amplifier? On the hard drive where numbers cool into permanence? Can a system be both undecided inside a box and decided from the corridor outside? And why does watching gently, again and again, sometimes hold a quantum system in place, as if attention itself could shelter a delicate flame? In the minutes ahead, we'll replace myths with mechanisms. We'll see how information becomes fact, how the environment itself, air, light, walls, broadcasts what happened, and why the universe's bookkeeping leans toward the irreversible. We'll meet thought experiments that unsettle and real experiments that guide. No equations tonight, only careful language, faithful images, and the humbling realization that to measure is not merely to peek through a window, but to help write a page of the world. If a single click can change the story the universe tells, then the question is unavoidable. What truly counts is looking, and how does looking shape? What is there to see? Dim the lights. Imagine a silent lab at midnight. On a sensor the size of a fingernail, one lonely pixel flickers to life. No one is watching, no fanfare, no gasp. And yet something has happened that wasn't true a moment before. A single photon arrived, left its tiny signature, and turned possibility into a fact. An observer in physics is not a pair of eyes. It's anything that leaves a mark, a crystal grain that darkens, a counter that clicks, a byte that flips from 0 to 1 and stays that way. Observation is the art of making a record, a trace that endures long enough for the world to point at it later and say, that. How does a ghost of a signal become a headline the universe can't ignore? The journey begins with a whisper. First, transduction. A photon jostles an electron. A passing particle leaves a whiff of ionized air. A faint magnetic tickle nudges a loop of wire. Then amplification. The timid nudge becomes a cascade. More electrons knocked loose, a chain reaction tumbling forward like a line of dominoes. Next comes latching. Some simple, sturdy mechanism decides, yes, this happened, then flips into a new state that won't easily flop back. Finally, recording. The result is copied into places that last. Silver grains in film, a glow on a phosphor screen, a time-stamped entry on a hard drive. From whisper to headline, from maybe to now we know. But there's a price for knowing. To take a pulse, you have to touch the wrist. In the quantum world, every question is also a nudge, however gentle. This isn't clumsiness, it's connection. You can't learn the temperature of a glass of water without your thermometer sipping a breath of its heat. You can't ping a distant airplane with radar without your pulse giving it the faintest tap. Information is a handshake, and even the softest handshake leaves a fingerprint. So we learn to choose how we ask. Sometimes we need a sharp answer. Use a strong measurement, decisive, all in. The system is driven to announce a definite outcome, and the ambiguity is pared away like a sculptor's final strike. The cost? We've changed the thing we measured. We won't get the old superposition back. Other times, we prefer a quiet hint. We use a weak measurement, so gentle, it barely nudges the system. One hint is noisy, nearly useless on its own. A whole chorus of hints averaged together paints a trustworthy picture while disturbing far less. A camera flash freezes a hummingbird's wings in mid-beat. A long exposure catches their blur without blinding the bird. Two ways to ask, two kinds of answer. If the act of measuring is a one-way street, why does it feel so irreversible? Because once a signal is amplified, it spreads. A single spark maps itself into a million electrons, into a glowing pixel, into a saved file, into a screenshot in a message thread. Those are copies, and many copies are hard to unwind. Try to unlight a whole city one bulb at a time, and you'll feel the arrow of time tug at your sleeve. Information, once widely shared, behaves like spilled ink. Theoretically recoverable, practically not. That practical irreversibility is why a shaky whisper becomes a stubborn fact. It's also why we need to retire a few myths. Myth 1. Observation needs a mind. Doesn't. A fog droplet that condenses around an ion track has observed a passing particle by writing a visible streak in midair. A camera chip that changes a pixel has observed a photon. Consciousness may marvel at the result, but the world does the writing. Myth 2. Observation means seeing. It doesn't. If a particle bumps into a wall and leaves a trace of energy behind, if light scatters off a dust grain and carries away the story of its position, that information has been laid bare. Whether anyone checks the ledger is irrelevant. The environment is a relentless witness. Myth 3. Observation is optional. In practice, it's everywhere. Air, light, walls, and warmth are busybodies. They gossip about systems all day long. Keep something isolated enough, and quantum strangeness blossoms. Let the world listen in, and those blossoms fold back into buds we call classical. Let's step into 3 rooms where we catch the quantum in the act. In the first, a cloud chamber rests under a cold lamp. A seed of alcohol vapor hangs just at the edge of condensation. A cosmic ray knifes through, leaving a trail of ions that coax droplets from the air. A faint silver line blooms and drifts, matter's most delicate autograph. No eyes required. The track is the memory. In the second, a single photon imager waits in darkness. The detector is wired to notice the tiniest electrical avalanche. One photon arrives, a controlled cascade follows. Lone pixel lights. Another arrives. Another pixel. Over minutes, a pattern emerges, one dot at a time. Each unassailable, you can save the file, transfer it, print it on paper. You have turned quanta into culture. In the third, the tip of a scanning tunneling microscope hovers a few atoms above a metal surface. A trickle of electrons tunnels across the gap, exquisitely sensitive to distance. By sampling gently, line by line, the instrument coaxes a map from the substrate, hills and valleys of electron density. Atoms like rounded stones in a stream bed. No big hammer blows, just a million careful whispers, aggregated into a portrait. Different devices, same story. Transduce, amplify, latch, record. And so we come to a deeper, subtler question. Where in that chain does observation happen? Is it when the photon first grazes the sensor? When the amplifier unleashes its cascade? When the bit flips on the drive? When a human reads the number? There is no single sacred line. The world doesn't stamp a moment observed in red ink. Instead, there is a process that grows from private to public. Early on, information is local and fragile. Clever experimentalists might, in principle, erase it. As it spreads into many electrons, into many atoms, into many machines, it becomes robust. At some point, the outcome is in the world enough that undoing it would be like trying to recall 1,000 whispered secrets already told. That's when we call it a fact. If that sounds less like magic and more like bookkeeping, that's the point. The observer effect is not a ghost in the lab. It's the accounting of information. Who has it, who could have it, how widely it's been copied, at what cost it might be erased. A measurement is a tiny story, becoming communal memory. And yet, even with all this clarity, a question waits in the hallway outside a certain sealed box. If an observer is any device that records, what happens when the device, the record, and even the air that carries the gossip are all locked away from us? Imagine a box on a table. Inside, a quantum trigger, a detector, a tiny mechanical hand, an entire measurement chain ready to make a fact. Also inside, something warm-blooded, whiskered, and asleep. From the outside, the world stands still. No light leaks, no whispers escape. Somewhere in there, did a fact already happen? Or does it become a fact only when we open the lid and let the story spill out? And what if, instead of a cat, it's a colleague, a friend, running a quiet experiment in a soundproof room? To them, the detector clicked an hour ago. To you, the lab is still in limbo. This fact is real. In the chapters ahead, we'll meet these paradoxes with open hands and steady eyes. We'll see how thought experiments sharpen our language, how the environment's constant attention hides quantum strangeness in daylight, and how different philosophies of physics try to reconcile private whispers with public truth. For now, remember the Midnight Pixel didn't need an audience. It needed a place to write its story. That, in the end, is what counts as looking. Hold a book near a window and watch the sunbeam. Tiny specks hang in the air, each outlined by scattered light. No one is observing in the human sense. Yet those specks announce themselves everywhere, on your retina, on the walls, on the camera sensor across the room. That is the intuition we need. In the quantum world, being seen is not about a conscious mind. It's about leaving copies, traces written into the surroundings. Begin with a single quantum object, say, an atom in a superposition of here and there. Let a detector listen for it. The atom's state becomes entangled with the detector's state, two possibilities braided together. Atom here, with detector here. Atom there, with detector there. But the chain doesn't stop. Air molecules collide, light scatters, vibrations creep into the tabletop. Each contact carries away a hint of which alternative is which. In moments, the information about here versus there is smeared across millions of degrees of freedom. Photons, phonons, and thermal jostles, spreading outward like ripples on a lake that never end. The system doesn't flip a switch from fog to rock. It hands out photocopies of its state to the room, then to the building, then to the sky. Quantum interference needs carefully kept phase relationships, the subtle alignments that let possibilities add or cancel. Entanglement with the environment hides those phases in a maze of countless correlations. From the system's point of view, the delicate alignments are effectively lost. Interference terms are washed out, not by a hammer blow, but by being diluted into everything else. Think of drawing a fine interference pattern on a chalkboard and then brushing it lightly with a sleeve, again and again. You never erase any one line decisively. You just blur it into background dust until the pattern can no longer be recovered in practice. That blurring is decoherence. It doesn't pick a winner, it makes the contest unplayable. Fundamentally, decoherence explains why we don't see cats half alive and half dead in daily life. The phases that would reveal both at once leak into the environment almost instantly, making that information inaccessible. Not all quantum states are equally fragile under this barrage of environmental contact. Some are naturally robust because the environment measures them over and over. These privileged survivors are called pointer states, the configurations that keep getting copied rather than scrambled. For objects in ordinary conditions, position is the standout. The air and the light in the room constantly sample where things are. Tiny differences in location scatter photons in noticeably different ways, so being at this place is the state that's redundantly reinforced. Momentum, phase delicate superpositions, and other airy possibilities get blurred. Positions and near-classical trajectories are what remain crisp. The environment is a relentless pollster that asks, thousands of times per microsecond, "Where are you?" States that answer clearly get reported. States that waffle get averaged out of the newsfeed. Why do we agree on what we see? Because the environment acts like a broadcast network. When a dust mote floats in a shaft of light, it scatters vast numbers of photons that carry the same headline, "Dust mote here, moving this way." You and I, standing on opposite sides of the room, can intercept different photons and still infer the same position. We never touch the mote. We read the news the environment is already publishing. This is the essence of quantum Darwinism. The environment doesn't just decohere, it duplicates certain information into many, many fragments. When there are enough redundant copies, multiple observers can learn the same facts independently. That redundancy is what we call objectivity. A story becomes real in society when it's printed in many newspapers, it's aired on many stations, mirrored across many sites. In physics, a property becomes classically real when the environment has printed the same headline on my photons, your photons and everyone else's. Decoherence is not a philosophical verdict, it's a physical process. It explains with no appeal to consciousness why interference vanishes for big, warm, noisy things. It explains why pointer states like positions dominate our everyday world, and why records are stubborn once written. But decoherence alone doesn't tell us which outcome is chosen in a single run. It tells us why the other possibilities become unobservable, why only one storyline survives in accessible records. Interpretations disagree on what that means. Whether the wave simply snaps, whether branches long continue in parallel, or whether facts are relations that crystallize when records meet. What they share is this engine. Entanglement spreads, phases hide, redundancy blooms. Here's a walkthrough you can picture. Scene 1, ripple to static. A bright interference pattern slowly gives way to snowy speckle as an air density slider rises. The more the system talks to its surroundings, the less the pattern can reappear. Scene 2, the broadcast. Single dust mote, then expanding rings. Each ring is a shell of scattered photons carrying a copy of where it is. Small cameras pop up at random points, each reconstructing the same location from the light that reaches them. Scene 3, the survivors. A lineup of states such as sharp position, sharp momentum, delicate superpositions. The environment's vote counter favors position over and over. The others fade like ink in the rain. Decoherence and quantum Darwinism give us a sturdy picture of how the classical world emerges. Possibility gets copied outward until only one storyline is left readable. We can now understand why observation doesn't require a mind, only a record, and why many minds will agree when they consult independent copies. But puzzles remain. What happens when two observers like Wigner and the friend hold incompatible records? How should we interpret experiments that let us decide after the fact which pattern to reveal? And can a single system carry a quiet, classical-style history between looks? Next, the mind-stretching tests such as Wigner's friend. Delayed choices, LIGO, and contextuality where we learn that quantum facts are not just fragile, they're about the questions we allow into the story. Here's your takeaway line for this part. We call it real when the environment publishes the same headline everywhere. In the soft glow of an isolated lab, a detector clicks. Inside, the friend writes photon detected. A fact has been born. Local, definite, archived in ink and memory. But now, step back. To Wigner, standing outside with his interferometer and extreme patience, the whole room, friend, detector, notebook, and air, can be treated as a single quantum object. If none of those inner records have leaked to the world, if no whisper of the outcome has slipped under the door as heat, light, or sound, then in principle, Wigner can test whether the entire room still carries quantum coherence. As if the friend's measurement never quite settled. Two descriptions. Inside, I saw the click. Outside, I could in principle reveal interference from the whole, which is the real story. The subtle answer is about records. If the friend's note or her brain state has entangled with the environment, if air molecules, scattered photons, or even gentle vibrations have broadcast her result, then Wigner's interference test will fail. Decoherence has already written the outcome into the world's margins. If, however, the room is so perfectly isolated that no trace is escaped, then Wigner's grand test may succeed, showing that from his vantage, no final fact existed yet. No paradox arises when we respect what each observer can actually access. The friend's fact is a fact for her, given her records. Wigner's experiment asks a different question of a larger system and can, in principle, get a different kind of answer. Only when the two compared notes literally bring their records together must the stories dovetail. At that moment, the broader world gains the same page. Modern laboratories have inched toward this thought experiment with entangled photons, superconducting circuits, and tiny quantum memories that stand in for a friend. Each confirms the same lesson. Facts live where records live. In short, a result can be definite for one observer and not yet for another. Consensus arrives when records meet. Here is a favorite riddle. Decide after a photon hits the screen whether it behaved like a wave or a particle. Surely that flirts with rewriting the past. We send photons toward two slits. If we leave them untagged, their arrivals form an interference pattern, ripples of light and dark that speak of superposed paths. If we tag the paths red for left, blue for right, the pattern collapses into two simple mounds. No interference. Now the twist. We route each photon's partner through a device that either reads those color tags or erases them. And we make that choice late, sometimes after the first photon has already landed. When we later sort the first photon's positions into piles based on what we did to its partner, something uncanny appears. The pile corresponding to tags erased shows interference. The pile corresponding to tags read does not. Did our late choice reach backward in time to change what the earlier photon really did? Nope. If you ignore the partner entirely and look only at the main screen, you never see interference, just a smooth haze. The interference appears only when you condition on the later information and sort the data accordingly. No signal travels to the past, no message outruns light. We are not rewriting history. We are rewriting which story is consistent with the records we agree to keep. In Wheeler's delayed choice spirit, quantum behavior isn't a costume sewn at birth. Wave-like or particle-like, it is a verdict delivered by the kind of question we finally ask, by which records we choose to preserve or erase. What it all boils down to is that late choices don't change earlier events. They change how we slice the data, and therefore which pattern our records reveal. Bell's theorem tests whether distant particles carry hidden, pre-agreed answers. The Leggettgard program asks a simpler, more intimate question. Does a single system carry a trajectory-like property at all times? A definite value you could, in principle, read without disturbing it? If such macro-realism holds, if things really do have pre-existing states, plus a way to peek non-invasively, then certain combinations of time-separated measurements must obey tidy bounds? Experiments with superconducting qubits, nuclear spins, photons, and mechanical oscillators keep breaking those bounds. Even when engineers use clever, negative result, or weak measurement tricks to disturb as little as possible, the data say no. The world does not, in general, come with all answers written in the margins, waiting patiently for us to lift the page. This is not a license for chaos. It is a reminder that values in quantum land are not simply there like ink on a ledger. They are coaxed into being by the contexts we create by which questions we ask, and when, and how gently. Fundamentally, for single systems across time, nature resists the comfort of pre-inscribed trajectories. What exists to be read depends on how and when we try to read it. Suppose you believe that every measurable property of a system has a definite value, independent of how you choose to examine it. The Koch and Specker theorems turn that belief into a logic puzzle. Find you cannot complete it without breaking your own rules. In everyday terms, the outcome you get can depend on which compatible questions you ask alongside it. It's not because the system is coy, but because the quantum fabric links answers together in ways no list of hidden entries can satisfy all at once. Change the context, and the web of relationships you probe changes as well. This contextuality is not just a philosopher's flourish. It has teeth. Experiments across platforms validate it. And theorists now count contextuality as a resource fuel for certain quantum computations that outpace classical rivals. The puzzle that forbids a universal context-free ledger turns out to power the very advantages engineers seek. Basically, in quantum mechanics, outcomes belong to contexts, not to a secret context-independent checklist. Wigner's friend tells us that facts are local to records until records are compared. The delayed choice eraser teaches that we do not rewrite events, only the story our kept records can consistently support. Leggettgarg shows that single systems do not carry a full script through time, ready for non-invasive reading. Contextuality reminds us that answers are braided to the questions we pose. Hold these together, and a sturdier picture emerges. Quantum theory does not license retrocausality, nor does it require a human soul to perform a mystical act. It says something more grounded, and perhaps more wondrous. Records make reality shareable. Before records meet, different observers can quite legitimately live on different pages. When records meet, single edition goes to print. But printing an edition, amplifying a click, copying it, storing it, protecting it, is not free. It takes work. It writes heat. It explains why facts resist erasure and why time's arrow feels so firm. In simple terms, measurement doesn't rewrite the past. It rewrites which past is consistent with the records we allow into the story. In the next part, we follow the cost of knowing. From Maxwell's demon to the warmth of data centers. We'll see why every observation spends a little entropy to make a fact, and why the universe's ledger of records points inexorably forward. In the quiet of a midnight lab, one click becomes a fact. And with that fact comes a whisper of warmth. It's easy to miss, but it's always there. Whenever the universe writes something down, it pays ever so slightly in heat. Tonight we follow the bill. We begin with a mischievous thought experiment. Imagine a tiny gatekeeper perched between two rooms full of gas. The demon watches the molecules. Hot, fast ones go right. Slow, cool ones go left. Soon, one room warms, the other cools, and our demon seems to have built a temperature difference from nothing. Free energy, a cheat code against the second law of thermodynamics. So what's the catch? The catch is the clipboard. To sort the fast from the slow, the demon must know which is which. It must store those decisions, even briefly little ticks in a memory. And when the page is full, the demon must clear it to keep going. That clearing, that erase, is where the bill arrives. You can juggle bookkeeping tricks as you please. But when you truly wipe information, when you make a many possible memory into a single clean slate, you pay the universe in heat. In other words, there is no knowledge without a ledger. Sorting, deciding, filing, these are not abstract acts. They are physical processes that leave physical scars in the form of entropy and warmth. The demon never beat the second law. It just hid the cost in the eraser. Now zoom back to our detector click, some microscopic event. One photon, one electron must become a macroscopic record you can scroll back to tomorrow. That requires amplification. A small nudge cascades into a big signal, tugging countless electrons into motion. The process is like turning a whisper into a stadium chant. Once a crowd has taken up the chorus, unchanting it, reversing every clapped hand, every breath of air is for all practical purposes impossible. In principle, with perfect slowness and care, some copies of information can be made with vanishingly small heat. But erasing information has a hard floor. Cleaning a memory to forget is an intrinsically lossy move. And in the real world, we also need records to be robust, to stand up to noise, temperature drift, and cosmic rays. Robustness means redundancy. Redundancy means extra copies. Extra copies mean more degrees of freedom involved, and more heat spilling into the surroundings. So the measurement chain, sensor to amplifier to memory, has an arrow. Tiny, reversible ripples at the start. Loud, irreversible outcomes at the end. A fact is not just a number, it's a record. stable, redundant, and retrievable. That stability is bought with physical work. The ink sets, the charge on a memory cell settles, the magnetic grains on a drive line up. Reversing all of those alignments down to the last molecule would mean undoing a vast swirl of microscopic motion. The universe knows how to go from tidy to messy in a million ways. It knows almost none to go from messy back to that exact tidy. This asymmetry is why facts feel like they only ever accumulate. Yesterday's photo sits on your phone, today's gets added. Diaries filled from blank to written. We can forget, yes, but forgetting is its own physical action, with its own heat. We often talk about time's arrow as if it belonged only to exploding stars and cooling coffee. But it threads through every act of observation. Each time we translate possibility into a record, we push a little heat into the world and take away a little ambiguity from our notebooks. The universe gets microscopically messier. Our story becomes macroscopically clearer. Stand in a data center and you can feel it on your skin. Billions of bits being written and erased each second. A planetary memory palace, humming with narratives paid for in warmth. On a smaller scale, your phone grows slightly warm as you record high-speed video. The sensor counts photons. The processor organizes them into frames. The storage locks them down. Knowledge is not free, it is engineered, and the engineering glows. Engineers have grown clever at peeking without poking. They cool sensors to hush random jiggles. They use trick light that's quieter and just the right way. They design amplifiers that dodge certain kinds of pushback. All of this can lower the cost of looking, sometimes astonishingly so. But the lower bound remains. Erasing information like resetting your counters, clearing your notes, still writes heat. And the moment you decide to promote a fragile quantum whisper into a stable many-copy headline that others can read tomorrow, you're choosing a path with a thermodynamic toll. You can make that toll small, you can move it elsewhere, you cannot make it vanish. Even ideas have footprints. The aha that jumps in your mind was carried there by neurons firing, ions pumping, calories spent. A telescope's revelation and exoplanets wobble. A distant merger's chirp travels through miles of fiber, racks of processors, and finally into a human archive. At each stage, the same quiet economics unfolds. Copy, amplify, stabilize, pay in warmth. There's an austere beauty to that honesty. Cosmos lets us ask questions, but it charges for the answers just enough to keep the books balanced. That balance is why perpetual motion machines remain in sketches, and why memory is precious, and why deletion is an act, not an absence. Let's clear a couple of myths. First, observation is just looking. No, observation is writing, creating a durable pattern that other systems can read. Second, a perfect measurement could be free. In practice, robust measurement needs amplification and redundancy. And erasing the intermediate notes has a fundamental heat cost. Third, the arrow of time is cosmic, not local. Well, actually, it is both. Every saved file, every logged particle track, every tick of a clock leans in the same direction. From atoms to archives, observation is more than a window. It is a tool that reshapes the world ever so slightly to make room for a fact. The reshaping is paid in heat. The heat is small, but it is honest. It is the signature of reality admitting this happened and arranging itself so that many witnesses may agree. Fundamentally, observation is work. To make a fact, the universe spends energy and writes heat. Imagine a dancer poised between two steps. If you clap sharply, again and again, just as the heel lifts, the dancer keeps resetting, ever quite leaving the floor. But change the rhythm of your claps, and the dancer moves sooner than they would alone. In the quantum world, attention itself can freeze motion or hasten it. Tonight, we learn to look without breaking, sometimes even to guide with a feather touch. If you're following this, you already think like an experimentalist. Well done. Start with a simple question. Can careful watching stop a change from happening? In quantum mechanics, the answer can be yes. If we make sharp, frequent checks, true decisive questions, the system keeps snapping back to where it was. This is the quantum Zeno effect. Many precise glances hold a state in place. like a metronome that restarts the bar before the melody can wander. But nature is subtler than a single trick. If we alter how and when we look, change the timing, soften the coupling, tune the environment, our attention can speed the change instead. That is the anti-Zeno effect. With the right cadence, watching helps the dancer take the next step. Why does this matter? Because delicate quantum states, the kind we need for sensors and computers, are forever tempted to drift. Zeno-style checks can stabilize them, hold an excited atom longer, keep a qubit from slipping. Anti-Zeno timing can accelerate transitions we actually want, like nudging a system into a useful state on command. The lesson is practical and human. Attention is not neutral. Its tempo and texture reshape what unfolds. If you've ever improved something by checking in often but lightly, then you already understand the Zeno playbook. Projective measurements, the loud questions, give crisp answers but end the dance. Weak measurements are different, or whispers. We couple so gently that a single reading is murky and barely disturbs the system at all. On its own, one whisper tells you little. But many such whispers, carefully combined, reveal patterns with astonishing clarity, while the system keeps gliding. With this feather touch, we can map a quantum state's tendencies, track tiny shifts in beams and phases, and even boost minuscule signals that would hide from bolder probes. Sometimes these gentle techniques produce weak values, averages that sit outside the usual range. Not because the world is cheating, but because we've asked a question in a very particular way. Prepare here, post-select there, and let the faint middle accumulate. It is less a paradox than a magnifying lens forged from statistics and restraint. Why use such care? Because fragile things, from single photons to superconducting qubits, break when handled with heavy hands. Weak measurement lets us learn without smashing, refine without ruining. It's how we weigh a whisper, not with one shout, but with a chorus of quiet listens. If patience is your strength, then this is your superpower. Stacking gentle evidence until truth emerges. That instinct serves science and people remarkably well. There is a third way to look. Not a single decisive question, not a series of feather-touch peaks that we average later, but a continuous listen, a stream of information that updates our best guess of the system's state in real time. Do this, and you can watch a quantum system trace a trajectory through possibility. A wandering path shaped by both its inner dynamics and your steady observation. With continuous monitoring, we become navigators. Each moment's data nudges our estimate. Each estimate informs the next nudge. Add feedback, tiny, timely pushes based on what we just learned, and we can steer. Keep a qubit aligned, calm a noisy oscillation, hold a fragile superposition on course against the gusts of randomness. This is measurement as a control knob, not a wrecking ball. It's the difference between slamming the brakes once and keeping a steady hand on the wheel. Engineers use it to stabilize quantum devices, cool motion with information, and catch errors as they bud rather than after they bloom. If you've ever guided a conversation with kindness, listening continuously, adjusting gently, you know this art already. The quantum version simply writes it into hardware. Push these ideas into many body systems, circuits where qubits are entangling, scrambling, and evolving, and a fresh phenomenon appears. The rate at which you measure can trigger a phase transition in the pattern of entanglement. Measure too little, and entanglement sprawls. Information weaves across the system, complexity grows like a vine. Measure too often, and entanglement shrivels. Threads are cut faster than they can form. The system becomes simple, local, almost classical. There is a threshold in between, sweet spot where richness survives yet remains readable. Cross it. And the very character of the many body state changes, not because of heat or pressure, but because of how much you look. This is profound. It says that information flow itself, what is copied, what is left unrecorded, can define phases of matter. For near-term quantum processors, it's a map. Probe enough to guide and learn. Not so much that you erase what you hope to use. Curate and you create. Here's a pocket guide you can carry into any quantum lab or any delicate task. Zeno Glance, Frequent decisive checks can freeze unwanted change. Anti-Zeno timing. The right cadence can speed a transition you desire. Weak peak. Ultra-gentle repeated looks reveal trends without wrecking the state. Continuous listen plus feedback. Steer in real time. Stabilize instead of stop. Measurement budget. In complex systems. Set a probing rate that preserves the entanglement you need while delivering the information you require. These aren't just tricks, they're a philosophy of care. Look with intention, and you will change less than you break, more than you fear. We began with a dancer and a clap. We end with a toolkit for grace. Freeze when needed, hasten when helpful, listen continuously, and choose a probing rhythm that lets complexity breathe. In the quantum age, the way we look is part of the law we live under. How we look decides what survives. Measurement can guide, not just end. You've just mastered some of the gentlest tools in the quantum workshop. Most people never reach this chapter. You did. In the next part, we put these tools to work, turning careful looks into clocks that define our seconds, sensors that weigh gravity's whisper, secure messages that tattle on eavesdroppers, and even computers that compute by measuring. We began with a simple idea, that the act of looking can make a fact. Here, that look becomes something more. A lever, a steering wheel. In the quantum age, measurement isn't merely a window onto reality. It's a tool we wield to pull whispers from the dark, to steady clocks that tame time, to compute by asking questions, and to secure secrets with the laws of nature themselves. If you've traveled with us this far, you're already thinking like the teams that build these instruments. There is a kind of noise the universe refuses to silence, the soft hiss of quantum uncertainty. For most of history, it set a hard floor under our measurements. Today, we push below that floor by learning how the hiss is arranged. Imagine that noise like a water balloon. Squeeze it along one direction, and it bulges in the other. With light, we can do the same. Squeezed light calms the fluctuations that matter for a given measurement, while letting their harmless partners swell. Point that calmer beam into a gravitational wave observatory, and suddenly, space-time ripples that once slipped through our fingers leave a trace we can hear. Not magic, craft. Now consider time, the quiet metronome beneath everything. An atomic clock counts a regular rhythm inside an atom. A transition so steady it keeps the world in sync. Navigation, communications, finance, science. The secret is not a bigger pendulum, but a better question. A probe so consistent that the atom answers the same way, beat after beat. The more precisely we ask, the more faithfully reality keeps time with us. And when measuring risks, disturbing the thing we care about, we get cunning. Back-action evasion is the art of listening to the combination that doesn't fight back, learning the information we need while nudging the system less. It's the difference between hammering on a piano to find middle C and touching just enough keys to hear the note emerge. Basically, we don't just read the universe, we tune the microphone. Some signals are so faint they seem untouchable. The magnetic field of a single neuron firing, a subtle change in gravity above a hidden cavern, a lone molecule binding to a protein. Quantum sensors make the untouchable tangible. In diamond, a tiny defect, one misplaced atom, can become an exquisite compass. Shine light, read the color of its glow, and you learn how a magnetic field is tilting it. These NV centers turn a gemstone into a stethoscope for magnetism, sensitive enough to map living currents or watch new materials as they form. Or let atoms themselves be the rulers. Cool a cloud of them until they drift like fog, split their matter waves, and let them meet again. Any difference in the path, gravity, rotation, a passing tremor, shifts the final pattern. It's an atom interferometer. A gravity map in a falling whisper, revealing what lies beneath our feet without a single shovel. At the scale of life, quantum readouts can register the moment a single molecule clicks into place. In that instant, one bond formed, one electron moved. An instrument crosses from mere observation into diagnosis, into discovery. If you're still here with us, know this. Curiosity like yours is the muscle that turns such lab tricks into tomorrow's tools. In short, with quantum eyes, the faint becomes measurable. We're used to thinking of computation as pushing, Gate after gate, operation after operation. There is another way. Prepare a carefully entangled resource, a woven state, and then compute by choosing what to measure and when. The heavy lifting is in the weave. The answer is brought into view by the sequence of questions you ask. This is measurement-based quantum computing. Each yes-no outcome nudges the remaining web into a new posture, guiding you step by step toward the result. It's less like forcing a maze and more like revealing a path that was there all along, hidden in the fabric. In more exotic materials, information can live not in any one spot, but in the global pattern, like a knot spread across a rope. Their measurement-only logic reads the pattern rather than jabbing at individual strands. Disturbances and local errors have a hard time untying a knot they can't find. The computation isn't fragile because the information isn't local. Sometimes the smartest move is not to push the system, but to ask it the right sequence of questions. Imagine writing a key in single photons. Each one is a messenger with a private orientation. Anyone who tries to copy a messenger must first read it, and that act leaves a scar. In quantum key distribution, you don't need to catch the eavesdropper's hand in the bag. You simply check the error rate. If it rises beyond a threshold, the laws of nature themselves have sounded the alarm, and you know you have to throw that key away. This is security not by obscurity, but by physics. From fiber links that connect cities to satellites that span continents, the principle holds because the principle is simple. In the quantum world, looking leaves a mark. In quantum security, detection is the defense. Behind every instrument in this chapter lies a small, sturdy recipe. Prepare. Begin with a quiet, well-understood state, a calm beam of light, a cooled atom cloud, a diamond defect ready to glow. Then, let it interact. Allow the thing you care about, gravity, a field, a biological binding, to nudge that state. Finally, read it out. Choose a way of looking that balances sensitivity against disturbance. Copy the answer into a durable record. There are trade-offs to mind. Turn up sensitivity, and you may invite noise. You may make the readout too strong, and you might crush the very signal you seek. But we've learned to bend those limits by correlation and cleverness, squeezing the right variable, sharing noise between parts so it cancels, listening where back action is quiet. Most people think quantum is smoke and mirrors. You now know it is checklists and craft. Good measurement is a triangle. Preparation, interaction, and readout held in careful balance. Now imagine connecting these instruments, clocks that compare their ticks across continents until they agree on time to the breath of an atom. Gravity sensors in a web that watch the planet's mass as it shifts with seasons, groundwater, and ice. An internet where the key resource is not bandwidth but entanglement, shared across cities so distant laboratories act like one. The future here is not a single breakthrough. It's a tapestry. Many small advances woven together. Cleaner light, quieter materials, better ways to store and forward quantum states. Each one widens the crack through which the impossible becomes routine. And if you've absorbed this chapter, you're already fluent in the grammar making that future. In a few words, as we link these instruments, the world becomes more legible. We began by turning a look into a lever. We learned to quiet noise when it hurts and amplify it when it helps. To ask questions so carefully that the answer arrives intact. To compute by measuring and to secure a message by the simple certainty that any stranger's glance will show itself. You don't just understand the idea, you can explain it. That matters. Here is your one-line takeaway. In the quantum age, the instrument is not a window, it's a steering wheel. Next, we'll face a calm but profound question. If measurements can build clocks, computers, and ciphers, what exactly is a fact when different observers bring their records to the same table? When those pages meet, what makes reality common ground? Stay with us. The universe is about to compare notes. A fact is not a thought, it's a footprint. Something stepped, something happened. The world left a mark you can find again. All episode we've watched possibilities narrow into outcomes, clicks and counters, lines and ledgers. Patterns that refuse to leave once they've arrived. Now we answer the quiet question beneath it all. What, precisely, makes a fact a fact? Here's a simple rule you can carry anywhere. The receipt rule. To graduate from rumor to reality, a record needs 4 qualities. First, robust. A gentle nudge can't erase it. The note survives a little noise. Second, redundant. It's copied in many places, so no single smudge can make it vanish. Third, retrievable. With the right tools, anyone can read it, not just the first witness. Fourth, reconcilable. Different readers get the same answer when they compare notes, if there's a receipt. Durable, duplicated, readable, and agreeing, you've got a fact. And if you already ask for sources, timestamps, and independent confirmation, you're closer to a physicist than you think. Curiosity and care are superpowers. Thank you for bringing them. There's another gentle distinction that clears a lot of fog. Private logs versus the public ledger. Before anyone compares notes, each detector, each lab, each person keeps a local diary. This is what I recorded. That diary is real for the tool that holds it, a local fact. But reality becomes common ground only when diaries meet, when independent records match. When my log and your log line up, we've built a public fact. It's the same move a newsroom makes when it asks for 2 sources, or a scientist makes when a different group reproduces the result. A fact for me becomes a fact for us when records meet and match. You may notice what's not on this list: a human gaze. In physics, observation isn't a mystical look. It's interaction plus amplification plus record. A Geiger counter in an empty lab is already a careful observer. A photographic plate remembers a particle's path whether anyone stares at it or not. People are exquisite detectors, curious, creative, meaning-making, but the universe can write in its own hand. Philosophically, though, we still have room to wonder how best to tell the story behind the receipts. Think of it as 3 lenses you can try on, different metaphors, same maths, same scoreboard of records. Lens 1. Objective collapse. Perhaps nature has a tiny built-in tendency for superpositions to snap into definite outcomes. Rare for atoms, frequent for elephants. If so, we can hunt for that snap in ever larger, quieter experiments. It's a bold idea because it's testable. If the snap is real, we will hear it. Lens 2. Relational or cubist flavors. Here, a fact lives between systems. Statements are about who interacted with whom. Probabilities are personal bets, updated when outcomes arrive. When observers compare records, their private stories reconcile, and a shared world emerges. Reality in this picture is what interactions agree upon. Lens 3. The pragmatic engineer. Don't pick a metaphysical fight. Build a better instrument. Use the theory, tighten the error bars, cross-check the data, ship the satellite on time. If the record is robust, redundant, retrievable, and reconcilable, it lives in our shared reality, good enough to navigate by, good enough to build on. 3 lenses, 1 scoreboard. Records you can't unwrite. So how do you use this? Beyond the lab. Here's a small fact-finder toolkit. 5 questions that work for physics, journalism, and everyday life. 1. Where's the record? Point me to the raw data, the log, the specimen. 2. How many copies? Independent labs, sensors, archives, redundancy matters. 3. Can I retrieve it? Methods transparent, access possible, steps repeatable. 4. Do the copies agree? Reproducibility is reality's handshake. 5. What did it cost? Real records leave footprints, energy spent, time taken, heat made. If making or erasing the record had a thermodynamic price, it's far less likely to be a mirage. If it leaves a trail you can follow, it's real enough to share. If you've ever double-checked a claim, asked for the source, or repeated a small experiment on your kitchen table, you've practiced quantum wisdom. You turned a private log into part of a public ledger. That's how civilizations learn. Let's gather the threads. A fact is a record the world has written in stubborn ink. Consciousness doesn't sprinkle magic. It brings meaning, questions, and the courage to compare notes. Interpretations offer poetry around the receipts, but the receipts themselves durable, duplicated, readable, agreeing. are where reality touches all of us at once. We began with a solitary click in the dark. We end with a chorus of clicks, a sky full of records. Through them, the universe not only reveals itself, it gives us a way to agree on what we find. In that agreement lies everything from medicine to spacecraft, from weather forecasts to whispered promises kept. Carry this with you. Be kind to claims, but kinder to evidence. Ask for the receipt. Celebrate when it arrives. And remember the line that has quietly guided our whole journey. Reality becomes common ground when records meet. Listen for a moment to the quiet. Somewhere, a counter ticks once. Just one soft click in a darkened room. That's where we began. A single photon choosing a detector, one trace scratched into memory. Now lift your gaze. That solitary click has company. Our world is a sky filled with them. Radio dishes logging pulses from distant pulsars. LIGO noting a tremor in space-time. Cameras counting starlight one grain at a time. We live inside an ocean of records. Tonight we've seen that measuring doesn't simply peel back a curtain to reveal a finished stage. It helps write the script we can share. Measurement is a promise kept, information copied, amplified, and made stubborn against forgetfulness. That stubbornness, what we called a fact, isn't magic. It is work done, energy spent, tiny notes filed into the universe's ledger until many readers, arriving by different paths, can all agree on what's written there. And here's the quiet marvel. You joined that work. Every time you insist on clarity, ask for evidence. Compare notes with someone who saw from another angle. You're practicing the same craft as our best instruments. You don't need a kilometer-long interferometer to be part of the story. Your attention is an instrument. Your patience is calibration. Your kindness, when you fold another person's observation into your own, is the art of building a shared world. We met the puzzle of observers and left superstition at the door. No special mind power is required to make reality behave. But minds are. Minds are remarkable because we can choose which questions to ask and how to listen. We can engineer gentle looks that guide rather than break. We can design experiments that let truth echo enough times to become common ground. In a cosmos where information is physical, curiosity is a renewable resource. You have it in abundance. Hold that thought and look outward again. The Milky Way is a library whose pages turn slowly, each supernova a punctuation mark, each planetary transit a footnote in a patient book. The universe notices itself through every trace left behind. Dust warmed by starlight, neutrinos threaded through rock, a fossil ring in ancient mica, the glow on a sensor in a midnight lab. When those traces meet, they cohere into the world we agree upon and call real. We'll close with a simple idea that points toward our next chapter. If facts live where records meet between system and detector, between you and me, then perhaps the deepest description of reality is not a list of isolated things, but a web of relationships. In episode 10, we'll follow that thread all the way down. How connections might build space, time, and the very notion of here with you. For now, take pride in the journey you've made. You stayed with difficult ideas, asked fair questions, and held two possibilities in mind until the evidence chose. That is not only good science, it is good citizenship in a shared universe. This is Cosmic Canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.